I'm also muting my. We can start, ma'am. I'm also muting my. Thank you.
Hello and welcome to the online info session about smart grids and emerging technologies. My name is Martina Waldner. I'm Senior Program Consultant at HECTOR School, which is the Okay. So, hello and welcome to the online info session about Technology Business School here of the KIT. I hope all of you can hear me well. I am here. So, okay, I'm very happy you are here today. With me will also be Professor Schmeck, who is professor here at KIT. And the topic smart grids and emerging technologies give you also a small insight into our master programs in energy and mobility, which we are offering here at KIT at HECTOR School. So probably you are not so well. KIT is not so well known to you. Let me give you just a brief introduction. So KIT is one of the excellent universities here in Germany with top ratings, and it's an engineering university. The main focuses of the KIT are information, energy, and mobility. And this is what we are also combining in our part-time master programs. KIT has a large number of employees, more than 9,000, and more than 6,000 of those are engaged in research and development. And we transfer this know-how directly into our master programs. Here in Germany, KIT is also known for generating innovation. This is a very big aim here in the university, and there are many spin-offs who contribute to society in the field of mobility, energy, environmental, every year here at KIT. So HECTOR School has been now for 15 years the Technology Business School of the KIT, and what we offer you are part-time master programs in English language, combining technology, management, and digitalization in our programs. And therefore, we really enable professionals, people with their first work experience after their bachelor, for a great career. We are the cooperation partner for many industries, for many companies here in Germany. And so therefore we have in very close touch also with the industry and what they need for employees today and in the future. So another input here on HECTOR School, then before Professor Schmeck will start with the session here today is, so we have 6 different master programs, and all of them are English taught, and they have a duration of about 20 months, 4 semesters, and you graduate with a KIT degree of 90 ECTS. We have our academy with further offerings here for professionals to gain technology know-how out of the research university. Yeah, really the strong focus is on the combination of engineering, management, and digitalization. And in the field of management, there is also many topics in the field of artificial intelligence or creating innovation. So in the field of technology thinking, and a very exciting roundabout here to pursue a master degree. So here the topic today will also is part of our energy engineering and management course, and we also have a course in mobility systems engineering. And this energy engineering master has a variety of hot topics like the power to X, power generation. Here we will cover all the fields from solar, thermal, wind, biomass, gas, and coal. There will be extra training planning on wind energy plants. Energy storage is a big part. And then what we're going to go on today out about smart grids, also in buildings. And you will see how energy systems are analyzed and what regulations do you face in the worldwide energy markets. Next to those engineering topics, there is a variety of management topics like project management, finance, strategical decisions, human resource, generating innovations, and therefore you will receive knowledge about different models who can be used to derive this information. Business law and intellectual property law will also give you a roundabout and really make the decider manager for tomorrow out of you. So, but now it's really time to give you what you are here for today, the topics of Professor Schmeck. And now I would like to hand over to you, Professor Schmeck, and welcome you here into the session. So Professor Schmeck will now continue with going on with an introduction about himself and will share now his slides for you here on this channel. Thank you very much.
Okay, there I am. I hope that you can see my slide now. I hope that my slide is shared. Can you briefly respond that I can know whether my slide is actually visible to you? Sorry, can you please?
So, yes, Professor Schmeck, your slides are visible. I also see it here on the YouTube channel.
Okay, perfect.
So this should be fine, yeah.
So, ladies and gentlemen, I'm very pleased to give you this talk on smart grids and emerging technologies. I certainly will only be able to give you a very brief overview of essential topics that we have there. And let me briefly start by telling you something about my name. So my name is Hartmut Schmeck. I am a retired professor of applied informatics at KIT, and I'm currently also or still a director of the FZI Research Center for Information Technology. FZI stands for Forschungszentrum Informatik, or in English, Research Center for Information Technology. My research areas are in informatics, so efficient algorithms, bio-inspired optimization, organic computing, which is about controlled self-organization, adaptive systems. And then the major reason why I am giving this talk is that in recent, around 20 years, I have been working on smart energy systems, and which led to an area which we call energy informatics. And you will see why we actually need that. My background in this area is shaped by participating in a range of projects, which I just highlight here. If you're interested, you can just Google for the different topics that are mentioned here, and then you get more information about that. So it's all kinds of projects, mainly having to do with decentralized energy generation and how we can deal with that, how we can integrate renewables into the grid, how we can actually integrate electric vehicles and their need for energy into a smart grid. And then also topics like security aspects of having actually more information communication technology in the typical power grid. We also have research infrastructures. For example, at KIT, we have the Energy Smart Home Lab, where you get more information on the link that I have shown there, Organic Smart Home. Organic Smart Home is an energy management software which we have designed and which is there at GitHub available. And we have at FZI, House of Living Labs, we have a living lab of smart energy where we actually operate the energy in that office building and also do research in that area. What will I present to you today? I will tell you a little bit about the background and the major challenges of the ongoing transition towards renewable energy sources, which is, like in Germany, called the Energiewende, but it's a global transition, which you also see in India, I guess, or as far as I know. Then the major topic is that for making that transition possible, we need flexibility, and there have to be new sources of flexibility, like load shifting. Electric mobility is providing quite a potential of flexibility, and we need energy system services. We need service providers which are different from the current energy system service providers, and I will highlight a few of the topics there and then come with a brief summary in the end. So let me start with just a view on what we actually had in Europe. Like, it's not the situation, as I know, in India, but in Europe we had for years a very stable energy system. So we have on several levels here, we have power transmission, power distribution, we have power consumption, we have almost constant voltage on several levels, we have constant frequency, very stable system, almost no blackouts. And we have central power generation here, large centralized power plants, followed by transmission, distribution, and consumption here at many different places. That's all the different places where we have power consumption. So this is the standard system. And in order to balance demand and supply, we have a very intelligent system of balancing the power. There's almost no need for communication because it's based on frequency deviations, so triggered by frequency deviations. Very intelligent system. So the question is why we actually need something different. The power prices were quite affordable, although much higher than for you in India. But in Europe, we had like really, for European standards, very affordable power prices. Now, why do we have changes? What kind of changes do we see? We have the change towards smart grids. And this can be characterized by the use of information and communication technologies for an increasingly smarter and more efficient power generation, transmission, distribution, and consumption. So ICT in the power grid. And if we talk about that, we have to talk about software architectures. And so this kind of architecture has been designed by a working group of the European Union, the so-called SGAM model, smart grid architecture model, which is characterized by 3 dimensions. We have different domains, as you can see down here, from generation over transmission, distribution, then distributed energy resources to the customer premises. We have different zones. We go from the process up to the market, and we have different layers, interoperability layers from the components over communication, information, function layer, and then the business layer. And so for any location here in that model, we need, architecture, we need to model the data. We have to talk about the different functions, about business objectives, and so on. This is a very systematic view on designing such complex software for the smart grid. But it does not mean that the grid actually is changed in its physical structure. So there's nothing different for the power grid, actually. It's just extended by this smart grid information communication technology. And the point is, or one point is, which is important to notice, that this actually introduces a new problem, which is actually the problem of cybersecurity. At the moment where you have a broad use of information and communication technology, you have to communicate over networks, and it means you are vulnerable. The smart energy grid is vulnerable to attacks on the information communication technology. But if you attack that, you also attack the power grid. And that really is something you have to be aware of. So it's vulnerable because of one point is that it is a centralized structure. And so you just have to attack the centralized components in order to have huge impact and huge blackouts if you are not aware of that. And then the point is that if you install something there, you really have to be using the security protection possibilities, and this sometimes is not done appropriately, and then there is the potential of attacks. So you could ask, why are we actually doing that, having had such a stable system as I mentioned in the previous slide? The problem is that we actually need information technology, and this is to quite some part due to the changes that we see. We have the climate change, and it means we have to do something about our power generation. In Europe, we had the energy technology targets, the strategic energy technology plan called 2020, actually with the target year 2020, which is now, but it was set out in 2007 by the leaders of the EU. It meant 20% reduction of EU greenhouse gas emissions, 20% share of renewables, of overall energy consumption in Europe, 20% increase in energy efficiency. So we are about at that point. In Germany, the targets were higher. In particular, we wanted to have 30% renewables by 2020, but this year 50% by 2030, 80% by 2050. And the main point is that this is a very strong move towards renewables. So this was actually phrased in 2010, and half a year later, we had the Fukushima event at the nuclear power plant there, and we had what we call the Energiewende, or energy transition, where we decided in Germany on a highly accelerated replacement of nuclear power with renewables by the year 2022. Like in the year 2010, we had 140 terawatt hours of power generation from nuclear power plants, which meant 22% of total power generation in Germany. And 2012, it was 90 terawatt hours, like the annual power generation. And 2022, it will be 0. So we have to replace that amount of energy, but we also want to replace coal and so on. So it's even more than that. And then in 2015, we had the Paris Agreement, which was the international agreement that we have to try to reduce the global warming to 1.5 degrees. And this is very hard to actually achieve. It is almost impossible now, I guess, but at least it tells that we have to be globally carbon neutral by 2050, which is quite a challenge. And we have to see what that actually means. It definitely means we have to move towards power generation from renewables. So what are the problems we have to cope with? One essential problem is the problem of fluctuations in demand and supply. But while we have been used to having fluctuations in supply in demand, this is shown here, like the red curve is showing, like in this diagram, it's showing the power demand and supply for 12 days in May 2010, and it's just showing typical problems that are occurring. So what you see here, as I said, the power demand in red, the daily changes, which are quite repetitive over the days, and there are weekly changes, like on the weekends, you have lower power. Here you have lower power demand. And then it shows the daily power generation from PV panels. It shows in yellow here the power generation from wind. And you see that there are quite a few interesting points here. You have the small-scale short-term variations over the day. You have then certainly the daily peak of power generation from PV panels. And then you have times where there's no wind. So here you have a dead calm over several days. And there are some days where you have a lot of wind, and here you have a lot of wind, you have a lot of sun, and you have very low demand. And that means you have a mismatch. You have more power generation than demand, which leads actually to negative energy prices. And this is a mismatch. And you have to cope with all these variations at different time scales. You can try to cope with that by demand and supply management. The problem is, what do you do with a dead calm? You cannot do anything with demand and supply management there. For that, you need storage or something which is a shadow power plant or something like that. So these are problems or fluctuations. And just to show you the current situation, like this year, we had quite significant power generation from PV. For example, here in week 32, 2020, like you can see the link for this chart. You see at the bottom here. You can just go to that link, and then you can see the situation at different times. But here, what I wanted to show you is that currently already we had times where we have here 35 gigawatt of power generation just from PV. You see that here at such a time, the power generation from coal is just 10 gigawatt, hard coal just 1, nuclear is just 7 gigawatt. That's very, very stable. You have biomass, very stable. And the fluctuating parts are brown coal, and then certainly like these fluctuations in the conventional fuels are caused by the fluctuations in renewable power generation from wind and from solar. There are other times where we have a lot of power generation from wind. So in the winter, actually here, not in the winter, in spring, in like mid of March of this year, we had 45 gigawatt power generation from renewables or from wind at this point here. But as you can see, very little power generation from sun here, just very, very small amount of PV power generation, and very little power generation here from brown coal, just 4 gigawatts. So here, a very small amount from renewable, from conventional power plants, most of it coming from renewables at this time. And then there are weeks where there's very little power generation from renewables. So here you see it's about like solar plus wind here, just 4 gigawatt of a total of 70 gigawatts. So it's less than 5% what we see here, and which is generated from renewables. Whereas overall, like in this year so far, we had more than 50% power generation from renewables, but not continuously. Sometimes very much, sometimes very little. And these are the fluctuations we have to deal with. The next problem is that these fluctuations are there, but it's very uncertain. We don't know exactly when they occur and to what degree they occur. So we have always the prediction of power generation in order to prepare for having the appropriate amount of supply for the next day. So we have predicted power generation, and I picked the day here of the like mid of June 2017, where we had a significant difference. So here, the predicted power generation for the day, at least here at 12 noon, so somewhere here at that time, was to have 20 gigawatt of PV power generation, 25 gigawatt from wind. And the actual power generation on that day was 25 gigawatt from PV and only 4 gigawatt from wind. So it means that there was an additional need of more than 10 gigawatt from conventional power plants. And this certainly is quite a change. So 10 gigawatt means it's more than the current power generation from nuclear power plants in Germany. And you have to decide from one day to the next, or within one day, that you need these more. You need this additional power generation from conventional power plants. And you have to be able to cope with that and to manage that, to provide this additional power. You don't want to shut off parts of the grid, but you have to supply the power, and this certainly is a challenge. So how can we deal with these short-term and significant deviations? Very often there are even much more short-term. Within half an hour, you might have significant increase in power generation from wind, for example, or from the sun, and you have to be able to cope with those changes. And then the third major problem that we have to look at, or that is actually significantly changing the way we are organizing the current power grid, is the decentralization, the large degree of decentralization. And what you see here is a segment of a rural power grid, a low voltage power grid, a low voltage segment connected to households here in the end in a rural area of the Black Forest in Germany. And at the end here, you have the effect of power generation from the rooftop, from rooftop PV panels. And it leads to power to voltage increase because the power line is not sufficiently strong, and so the power that is generated here cannot flow over that line significant or sufficiently, and so the voltage is increased quite a large amount. So you have a bottleneck here. The interesting point is that at the substation, you don't see that. At the substation, you have the normal voltage of 235 volts. And then you have a different situation. Let's say at the same spot, you have electric vehicles which have to be charged, and so you have a strong demand for energy, but the power line is not built strong enough. It's indicated in yellow here, so you have need for electricity, but it's not satisfied, and so you have a voltage decrease at this point. Again, at the substation, you almost don't see it. You're still very close to the normal voltage level. That means that you have local effects, you have local changes of voltage. Frequency will still be okay, but the voltage is really changing. The question is how you can deal with that. It's not sufficient to say at one segment, I have power in feed, and in another segment, I have power demand, and so this can even out. You have to either make the grid much stronger so that the power can flow without bottlenecks, or what you could do is you can just have this at the same location. And if this is the same location, and you know that there will be power generation from PV, and there will be electric vehicles available which need to charge their batteries, then you just let them recharge the batteries while there is this power generation, and then you are resolving that problem. But it means that you need really local problem solving at the location of the end customer. This is something which is very new to the power grid, which means it's a complete change to the way we organize power engineering for tomorrow's grid. So if we talk about energy management, we have to talk about balancing demand and supply. And the traditional assumptions are that the demand cannot be controlled, electricity cannot be stored, certainly cannot be stored in the grid. So the standard principle is that supply follows demand. So we do that by having predictions, day-ahead predictions, also months or years prediction, but also day-ahead predictions. We have intraday markets and so on. We have spinning reserve, primary, secondary control based on frequency deviations, and which this is a perfect system which worked fine for this kind of system. And now we have the changes that all of a sudden we have supply also at the low voltage region, and we have a potential reversal of power flow, which means that power is now flowing from low voltage to medium voltage to high voltage, which the grid has not been built for. So what we need now is that although we assume demand cannot be controlled, now demand has to follow supply. This requires much more flexible demand, which so far was assumed to be unflexible. And we also have to cope with this strong decentralization of energy management. We have to do something locally, which so far was not necessary. So these are the challenges that we have to address when we talk about shaping the future power grid. So what does this actually mean, this need for flexibility? So this is really a large problem. So we have the annual, like here I show you the annual duration line of electrical load in Germany, which means that all the time you have to supply at least almost 40 gigawatt, sometimes more than 80 gigawatt. And now we subtract the power generation from renewables, and we get the remaining power that has to be supplied from conventional power, like in the year 2014. And you see, okay, that reduced. Actually, one effect is that the difference between the lowest power demand from conventional, the highest power demand from conventional power plants is now larger. It increased from 43 to 62 gigawatt. That's the flexibility that has to be available from conventional power plants. And now if we look at the predicted residual load in 2050, it means if we subtract the potential power generation from renewables in the year 2050, we have a line like this. And this now shows that most of the time we have a huge surplus of energy, huge surplus, but there is this region here where we have a deficit. We still have a deficit, and it means that we will have abundant energy, but not always at the appropriate time. And the challenge is that those times where we don't have sufficient power generation from renewables, in some way we have to utilize the power that is there in surplus or potentially in surplus at other times. And this is the flexibility that we need to satisfy the demand that we have at those times from the surplus that we have at other times. Okay, so there are many trends in power generation. We have like power consumption is increasing worldwide, although energy intensity is reduced. We have low power smartphones, for example, or low power devices, but the number of devices is increasing. The share of renewables definitely has increased tremendously. We have more than 50% now. Power generation from fossil fuels will be phased out by regulation and by increasing carbon dioxide pricing. We have special effects this year by the corona crisis, like power demand is going down significantly this year. And in the long run, the power sources will be renewable, but there will be this need for shadow power plants, which I just highlighted to you. And recently, people talk about hydrogen and about synthetic fuels, but you have to be aware of the fact that if you talk about green hydrogen, it means that it has to be generated from green electricity, which means you have a huge additional demand for electricity from renewable sources. And this is another real challenge. You need even more power from renewables if you want to have green hydrogen. So the question is how we can actually create flexibility in demand and supply of energy. So we have to discover degrees of freedom with respect to time and size of power consumption generation. We have to observe the relevant components. We have to ask those who actually control them, the house owner who wants to operate his washing machine, or the industrial engineer who's operating a production line and can maybe can modify it. We have to exploit the information cloud flexibility to adjust the load profile, balancing supply and demand. We have to utilize storage capacities. And this can only be done by using information and communication technologies.
Professor Schmeck, I'm sorry for interrupting, but I have one question that maybe could correlate. A question that I would like to mention to you, and there was the focus on hybrid and electrical vehicles and how the smart grid technology can be integrated there. So I wanted to give you this question, so in case you want to briefly go on to this.
In a few slides, I will talk about electric vehicles also very briefly. Yeah, so you will see something about that just in a moment.
Thank you.
Yeah, okay. So in addition to the normal power grid, which is indicated in red here, we will see we have to see the information flow on the different related to the different levels of the power grid. And the challenge is to actually have sufficient information flow on the lower levels. We need something which we call an energy information network with distributed system intelligence. It means at the individual houses, we have to do something in an intelligent way. It's not sufficient to do something at central locations. Actually, the distribution grid nowadays should be called the collection and exchange grid, because it's no longer about distributing power that has been generated centrally. It's about collecting power that has been generated in a decentralized way, has been generated locally, and use that or exchange it with your neighbors and so on. So what we need more information on appliances, on storage, on generation facilities by having intelligent metering devices. We have to use that information. We need system platforms where we collect all the data and then design services for that. We have to look at our smart homes where we know everything about our local power generation, about demand from electric vehicles. We know something about our stoves, our washing machines, and we know something about the demands of the balancing responsible party, about the markets situation. And the question is what kind of information we have to exchange. So we are addressing this to more extent in our courses. I have to speed up a little bit. But like one point is like where actually we need the system intelligence. So if you have to like
sessions than this, and
Yeah.
there are also.
Okay, so I can continue, I guess. I hope, I don't know, at what slide did you actually lose connection?
Professor Schmeck, this was on slide number 19.
Okay, so I will just continue with this slide, with slide number 19. And so I talked about the problem that you have to decide whether you do information processing or take decisions locally in the smart home, or whether the power provider, for example, does the accounting and billing. And the point is that most of the information that is necessary to do the accounting is available in the smart home, and so could be done there, but then you need appropriate software at that location. And but it means it's not really necessary to send all the information to the power provider and let him do the power or the information processing. So this is something, to what extent you actually decentralize the information processing in this architecture. And then we have to look at another point, that we don't have only the power grid, but we have also a gas grid and a heat grid, which are connected. So if we have a surplus in the power grid, we could, for example, use electrolyzers to generate hydrogen. We can do methanation and get gas. And if there is a deficit in power generation, we could use the gas in combined heat and power plants and generate electricity, or at the same time generate heat. And we could also use extra surplus of electric energy to use a heat pump and generate heat directly. So there are transformations between power, gas, and heat, which are interesting and which provide more sources of flexibility. The point is that so far these areas are managed separately, but there should be an integrated energy management. So this is something which we have to design. So we need these integrated energy management systems. We need to balance demand and supply within each grid, but also have to convert energy between gas, power, and heat. To do that in a real conversion, that means power to gas, electrolyzers. You could also talk about virtual conversion. For example, if you have a surplus of power, you could just stop producing heat from gas, but produce heat from power, and vice versa. And so you could have some kind of virtual conversion in bivalent systems. But what you also need is interoperability of energy management systems for these different grids. For that, you need standardized interfaces, so lots of things to do for us. And then we certainly need this integrated energy information grid with distributed system intelligence. So the challenges for tomorrow's energy management are that we have to discover and exploit degrees of freedom and leeway for demand and supply management. We need adaptive energy management without reducing personal comfort or industrial productivity. And we have to develop new ways of storing electric energy in batteries. Power to gas is one point of storing energy. We need virtual storage. And all this has to be done in a reasonable way. So we need load flexibility and load shifting. The question is where we can get that. We get that by looking at smart homes and buildings. We can have appliance load shifting. We have electric vehicles. Now I come to the question in a moment with respect to electric vehicles, which can provide grid to vehicle or vehicle to grid scenarios, electricity from the grid to the vehicle or the other way around. And we have industrial processes, so we have to exploit the flexibility potential. So if we look at the potential of electric vehicles, what does it mean? So most electric vehicles are used just only to a small extent. They are used for about 1 hour per day. Like this is the result of a very broad survey. 94% of the trips are less than 50 kilometers. The net capacity, like storage capacity of the batteries, are around 40 kilowatt hours. And so if we look at the potential, if 1 million battery electric vehicles would be connected to the grid, we would have 40 gigawatt hours of storage available. If they are connected with single phase at 16 amps, we have 3.7 kilowatt power there, which means that with 1 million vehicles, we would have 3.7 gigawatt potential power, which is about equivalent to almost 3 nuclear power plants. And meanwhile, we even have 11 kilowatt connections or 22 kilowatt or even 150 kilowatt, but that's then DC, not at homes. But it means that the potential power that could be provided from electric vehicles is quite significant. If you see 3.7 gigawatt, if they would all be connected for 10 hours, they could provide electricity for 10 hours. Although they would be connected as a low voltage grid, and I mentioned the problems that we have there in transporting the energy into the grid, but they could provide power locally. It means we have high demand for power, but definitely, but also maybe high supply if power feedback is possible. The average time for charging, like if the battery is completely empty, it needs about 10 hours with 3.7 kilowatt recharging. If we have 22 kilowatt recharging, it's about 2 hours to get those 40 kilowatt hours again. But that means then we have quite a high risk of grid overload. And so we have a high flexibility for load shifting, like we have a long time where the vehicles are parked. And we have this time for recharging the batteries. That means high flexibility for load shifting here, but also the problem of potentially very high peak load. And we have to do something in an intelligent way to cope with that. And it will indicate that in a bit simplified way. So here you see such a peak load. If all the electric vehicles come home in the evening hours and try to recharge the batteries, we have this extra peak load in the evening, which we have to prevent. What could we do? We could move the power reach or the battery recharging to the nighttime hours where we have less demand from homes. Like the black line here is the demand, the traditional or the standard demand curve in some small living area. And if we look at the daytime, we have power generation from PV. We could utilize that to recharge the battery. And in the evening, we actually could use the battery to reduce the evening peak of power demand. And so what we could actually get is something which is indicated here in the green line. It's an almost stable power demand, which is visible for the grid, just by using the battery in an intelligent way, the batteries of electric vehicles. It essentially means that if we exploit the flexibility of battery charging, this could allow to generate a range of different demand profiles. And that's the main opportunity that we have to exploit here by intelligently managing the recharging of batteries. It certainly means that these vehicles have to be connected to the grid for quite some time while they are parked. It means we need a lot of connection points. But then we can actually do that in an intelligent way. And it means there are also numerous business opportunities for utilizing those opportunities for providing services which intelligently control the recharging of batteries and the use for vehicle to grid and grid to vehicle scenarios. Okay. So what we need is energy system services. We need services to stabilize the frequency. We need services to stabilize the voltage. We also need services for trading flexibility on the short-term spot markets. And I will briefly indicate what it means to stabilize frequency. So we have frequency control by load balancing. We have the primary controls, secondary control, minute reserve, which are also called frequency containment reserve, automatic frequency restoration reserve, and manual frequency restoration reserve. And they operate in this cascaded way, like primary control is on all the time. responding to frequency deviation. Secondary control is called on demand, and minute reserve also called on demand, and the hour reserve at the end if it's really necessary. And so there are certain minimum sizes that have to be contracted. We have to be able to cope or to cope with the failure of the largest generation unit. Like this, that's the traditional assumption for a power grid made up from renewable power sources. We have to change that slightly, but it means like we have to contract, or we need contracts with providers of control power to quite some large extent. This is just showing the timeline for the use of those control powers, primary, secondary, and minute reserve. And I want to briefly show you what it means to provide flexibility services at an industrial site. So we looked actually at a larger industrial site in Germany with quite some large power consumption, 210 gigawatt hours per year. There they have local power generation, combined heat and power plants. They have wind power plants there. They have a large battery facility, 12.5 megawatt power, 15 megawatt hours capacity. And they have flexible energy consumers. And then the question is how you can actually utilize that. And we showed that if you use frequency control reserve, like primary control, secondary control, if you operate on the spot market, do peak shaving and local energy optimization, you can actually save up to 12% of the energy bill, which in this case meant an annual saving of 2.5 million euro just by providing energy services. And this shows there is not only a need for the industry providing flexibility services, but industry actually can reduce their energy bill by providing those services. And this is really an opportunity, it's an incentive to actually doing that. And it's necessary in order to cope with the challenges that I mentioned in the beginning. So there is a need for aggregators. Why is there a need for aggregators? Decentralization, which I emphasized, means that we have many small providers of flexibility.
Professor Schmeck, I'm very sorry for interrupting you, but I just, the last 5 slides, they have been not transformed. I did not see them on my screen here.
Oh.
So, so therefore, I would just, wait for a brief second. I think the voice is fine, but maybe we can also use the time to answer a question.
Yes.
And we got a question in, and that said, how can we increase the next capacity of battery in electric vehicles with the implementation of V2G?
Well, so I will just go to the end then with my slide, and even if it's not visible, what I just want to briefly mention, I will come to the question in a moment, is that even if you don't see the slide, maybe you can see it later on. Is that all of what I've told you about means that we need a very transdisciplinary approach of power and control engineering, of informatics and communication engineering, of energy economics and law. And what we do at HECTOR School is that we address that, and we provide in our programs exactly that combination of different disciplines, of different competences. And so I guess that in our programs there actually provide a basis, provide competences for coping with these challenges. Now, the question was about how to actually improve the capacity of electric vehicles to provide these grid to vehicle services. Well, what you need is certainly you need electric vehicles you need vehicles which have batteries. They should have large batteries, certainly to have a large driving range, and then they need power from the grid. And so the question is, well, in order to provide flexibility, they have to be connected to the grid for a longer time. So all the time they are parked, they have to be connected. And then you need some intelligent electric vehicle supply equipment, like the environment, the charging station, and the electric vehicle operator, the controller of those charging stations, and the energy providers. They have to provide the flexibility in controlling the charging of the electric vehicle. So there are protocols which have been designed, like the IES 15118 protocol, which allows for negotiating a load profile between a vehicle and the charging station. A load profile which actually considers the demand of the vehicle and also the current situation of the local energy system. And so the load profile or the charging profile will be adjusted to the local situation. This is possible, but it needs the capability of the vehicle and the supply equipment, the charging stations, to actually negotiate such a load profile. The protocols for that are there. They are internationally agreed upon, but so far they're not really available on the market. So this is something which has to be done. If you don't have that protocol, what you could do certainly is let the power provider just control the charging power such that they never use too much power, but it's always adjusted to the availability of power that is there locally. There are other approaches where the vehicle providers, like the car manufacturers, actually want to decide on the load profiles. And there's quite a large need to actually come up with solutions for that. I guess that there will be different solutions in different areas of the world, but the best way is to be able to negotiate between vehicles and local electric vehicle supply equipment to adjust the charging to the local needs. And then we can provide exactly the services that are necessary.
So, and Professor Schmeck, I would also like to read out loud another question for you. So there was a question coming in, as India is having frequent climate change conditions, how can we apply this effectively in our country?
Could you repeat that, please?
Yeah, as India is having frequent climate change conditions, how can we apply this effectively in our country?
Well, you have like different climate or different weather conditions everywhere, I would say. And so there are times where you have more sun, times where you have less sun, like we have that in Europe, but you have certainly different situations in India. And it's just the necessity to, or the opportunity and the necessity. There's the opportunity to exploit the solar radiation and also wind, as long as it is available. And then, as I said, store that energy in some way, either by large batteries or by, like if you have surplus, transform that into hydrogen, or in some other storage facilities. And then at times where you have less solar radiation because of the times where you have a lot of rainfall, very little sun, there you need then to use that storage facility. And so, like for India, I see interesting opportunities to actually, like if you're building now a new energy system, a new power grid, because there have been areas which did not have access to power to electricity so far. And it would be the wrong direction if you would try to build something which is similar to the traditional grid we had in Europe. Your opportunity is to right now build the grid that we envisage in Europe for the future. So a very decentralized grid where you build up the grid bottom up, and you have to be able to respond to the local weather conditions, definitely. And so you need to build up storage or power generation facilities, storage facilities, like a lot of local battery installations. And this actually is facilitated by the rapid decrease in prices for PV panels, for battery cells, which makes it possible to actually install this and utilize that in an economical way.
Thank you, Professor Schmeck. And then I would like to read another question, and this is, how can we implement smart grid integration in a country like India? So maybe this would fit to the question before.
Yeah, so I would say that you should utilize the opportunities of renewable power generation. And it means that you need local energy management systems, you need local control of the energy. You will certainly also need long-range power lines. But the essential point is that you want to provide power to your people. And for that, you need to utilize the opportunities that are there locally by utilizing PV panels, by using wind power plants, and maybe also to some extent biomass as far as it is possible. But the best way at the moment is to build up a decentralized system bottom up gradually, but that provides very fast power to, or in a very fast way, power to local people. It may not be that stable in the beginning, but as far as I know, your current characteristics of the Indian power grid are different with respect to stability from the European standards. And so you definitely can improve the power generation by utilizing the potential of local power generation. And you have to extend that more and more, and you need local energy management systems, which we designed for our future power grid, and it would be available for your power grid that you read right now. So in some way, I could say that you can actually make a jump towards the technology that we envisage in Europe for, like to have in 10 or 20 years. You could build that right now.
Okay, and I would like to read another question for you out loud, Professor Schmeck, and this is, how can we integrate smart grid for our hybrid and our hybrid and electric vehicles? Okay, how can we how can we integrate smart grid technology for hybrid and electrical vehicles?
Well, that's what I mentioned already. Like when we talk about smart grid technology, we talk about having intelligent energy management systems. And we need those intelligent energy management systems if we want to integrate the needs of electric vehicles, because we have to satisfy the demand for local customers. We also have to satisfy the demand for the vehicles. And we have to get a match between that. Yeah? So we have to do that. And sometimes it may even be that there is a local need for power which cannot be satisfied by the grid, by the local grid, but the electric vehicle is standing in front of the house or in a living quarter, and you could utilize actually the energy from the battery in order to provide power for the house. But for that, you need the ability to actually feedback energy from the vehicle into the grid. And it means you need an inverter to do that. So you not only need a charging station to charge your battery, you also need in the charging station an inverter if you want to feedback energy from the vehicle into the grid. But this is something which can be designed, which is available. And if you have that, you can use the electric vehicles in a very flexible way, and it provides additional opportunities for utilizing the electric vehicle. So in particular, in an area where you have fluctuating demand and supply, electric vehicles provide this source of flexibility that is actually needed. But then the battery would not only be used for providing you with mobility, but also with providing electricity at some times for your home. And this needs intelligent energy management. The systems for that are being developed currently, have been developed in some cases. We have tested that in projects, and we certainly talk about that in our programs.
So thank you very much, Professor Schmeck. Then I would close the round for today. To all the participants, thank you very much for your attendance and your interest in the topic smart grids and emerging technologies. If you have any questions, feel free to get in touch with me, with us. I also I dropped down my email here in the chat. So we are happy to hear from you, and we're wishing you all the best, and please stay healthy. Thank you very much for today. Bye-bye.
I would like to mention also that I hope that you got something out of my talk. I'm sorry that we had these technical problems. I hope that you could listen to me at least. And the slides of the talk, I guess, will be made available as a PDF, so you can look at them afterwards. Okay, thank you very much. Bye-bye.
Bye-bye.